In the silence between galaxies, where light thins and matter fades, space reveals a truth most never hear. The universe around us looks bright and crowded in every direction, filled with stars, nebulae, clusters, and distant islands of light. Yet behind that familiar glow lies a far more unsettling reality. The space we inhabit is not dense, it is not typical, it is not even average, it is hollow. The Milky Way drifts inside a massive underdensity, a region so vast that no human word carries its full weight. 2 billion light-years across, a cosmic hollow carved out of the universe itself. A void so large that every map of nearby galaxies bends inward around it, like the edges of a drained ocean. For decades, the assumption was simple. We lived in a normal place, in a normal part of the cosmos, surrounded by typical structures, but the deeper astronomers looked, the more this assumption cracked. Space around us was not behaving as it should. Velocities drifted, light slowed, galaxy counts dropped, and a strange expansion rate appeared in every direction. The evidence was impossible to ignore. Something enormous was missing. Something vast and silent was enveloping us. The KBC void. Our cosmic neighborhood is not a cluster, not a filament, not even a neutral region. It is a hollowed pocket in the universal web. And inside this emptiness sits Laniakea, a supercluster of 100,000 galaxies suspended like a floating lantern in a desert of space. But even this raises a deeper question. How can a massive structure, one of the largest known, exist inside a region defined by its lack of matter? The answer lies in scale. Zoom out far enough, and even enormous superclusters shrink into small beads scattered through an ocean of space. Zoom in close enough, and the void is not empty at all. Filaments thread through it. Clusters gather along those threads. Galaxies circulate inside those clusters. Stars ignite within those galaxies, and planets form around those stars. Structure exists at every scale, but the balance between them is uneven. The void is not a hole in the traditional sense. It is a reduction, a thinning, a cosmic breath drawn inward. On average, there is roughly 20% less matter here than the rest of the universe expects. But averages blur detail. They hide the filaments and the flows. They hide the slow gravitational tides that pull galaxies toward massive attractors far beyond our view. Within this thinning region, rivers of matter still flow. Laniakea is one such river, stretching 300 million light-years, guiding galaxies toward a deeper gravitational well far beyond its edge. Gravity sketches boundaries in motion. The galaxies streaming toward a dense region called the Great Attractor mark the outline of Laniakea like currents defining the shape of a great ocean. Everything moving toward that distant mass belongs to the supercluster. Everything flowing away belongs to structures beyond. The Milky Way's own motion, hundreds of kilometers per second, confirms it is part of this vast network. But even Laniakea is not the final station. It too is falling. A larger beacon pulls on everything around it. The Shapley supercluster, a titanic accumulation of matter so massive that space bends subtly toward it from 600 million light-years away. Gravity builds hierarchies. Galaxies fall toward clusters. Clusters fall toward superclusters. Superclusters fall toward even greater structures stitched into the cosmic web. And in an underdense region like the KBC void, this motion becomes even stranger. The void pushes outward while gravity pulls inward. Expansion and attraction combine, twisting galaxy velocities into patterns far more complex than simple cosmic expansion. This is the first clue that something enormous surrounds us. For decades, astronomers assumed the accelerated expansion rate measured nearby was universal. But the numbers did not agree. Close measurements suggested one speed. Distant measurements suggested another. The deeper the view, the slower the expansion seemed. This mismatch, the Hubble tension, whispered that something was wrong, and the growing suspicion was simple. We are measuring the universe from a distorted location. Inside a void, galaxies move outward faster than average because there is less matter pulling them back. Light from these galaxies carries that motion with it. When measured from our vantage point, the universe appears to expand faster than it truly does. This effect can mimic new physics, new energy, or even modified gravity. But the simplest explanation is also the most unsettling. We live in a region where the fabric of space is thinner than normal. The discovery reshaped everything we thought we knew about cosmic expansion, structure formation, and even the age of the universe. Because a faster local expansion rate makes the universe seem younger. Younger than the oldest stars, younger than the oldest clusters. A paradox created not by physics failing, but by perspective misleading. The next step was to map this hollow. To see it not as a concept, but as a structure. Massive galaxy surveys traced its outline. Peculiar velocities mapped its interior. The cosmic microwave background revealed its imprint. Even ancient sound waves frozen from the early universe. Baryon acoustic oscillations formed a cosmic ruler that confirmed the underdensity surrounding us. Every line of evidence pointed toward the same conclusion. A vast, quiet region envelops our galaxy, stretching far beyond anything the naked eye reveals. And so the paradox dissolves. A supercluster can exist inside a void because the void describes billions of light years, while the supercluster describes hundreds of millions. Large-scale emptiness and small-scale structure can coexist in the same cosmic volume. They must. The universe is fractal in its architecture. Dense knots embedded in thin regions. Bright islands in dark oceans. Light suspended in the silence. In this hollow landscape, the Milky Way drifts not at the center, but offset. A resident of a moderately dense pocket inside a much larger underdensity. We are not isolated. But we are surrounded by more emptiness than most regions of the cosmos endure. And the deeper we explore, the more the void shapes every measurement we make. Yet one question remains, hanging in the darkness like a silent echo. If this giant hollow shapes everything we see, how much of the universe do we truly understand? And how much has been distorted by the emptiness surrounding us? The journey outward starts with a single step, a shift in perspective. To understand the vast hollow surrounding us, you must leave the familiar boundaries of the Milky Way and follow the threads of the cosmic web into the dark. As you move away from our galaxy, the first realization settles in. The universe grows quieter, not louder. The crowded star fields thin. Neighboring galaxies drift apart. And the structures that seemed close from Earth reveal their true separations. Millions of light years of nothing stretching between them. This silence is the signature of the void. From a distance, the Milky Way looks like a glowing whirl suspended inside a faint mist of other galaxies. These companions form the local group, a small association bound by gravity, moving together as one drifting island. But even this group is not static. It is sliding across space, pulled by gravitational forces from beyond, pushed outward by the underdensity behind it. Every motion points to a deeper truth. Space around us is uneven. As you follow the local group outward, you glide into the surrounding region known as the local sheet, a thin plane of galaxies stretched across tens of millions of light years. Their motions form a pattern, all drifting in the same direction, all responding to the same distant pull. The sheet itself is gliding away from a nearby underdense pocket called the local void, one piece of the larger KBC supervoid. This drift is not random. It is the void revealing its presence through motion. Continue farther, and the structures sharpen into clearer patterns. Galaxies arrange themselves into gentle arcs and filaments. These are the threads of the cosmic web. They define where matter prefers to gather. But here, the threads grow thinner. Clusters become sparse. The empty spaces between them widen. The web loosens its grip. The challenge emerges clearly now, to map a region defined not by what is present, but by what is missing. Measuring a void is unlike measuring anything else in astronomy. You cannot simply count galaxies and declare a structure empty. The universe is vast, and galaxies are scattered irregularly everywhere. The first test is to determine whether the emptiness is real or only apparent. Is the underdensity a true feature of space or a coincidence of perspective? Astronomers met this challenge with one crucial tool: scale. They expanded their surveys outward, sampling millions of cubic light years at a time. And at every increasing scale, the same pattern appeared. Fewer galaxies than expected, fewer clusters, fewer filaments. A systematic drop, not a random one. The void was not a trick, it was a structure. But the discovery did more than confirm emptiness. It revealed tension. A tension between what models predicted and what measurements showed. Simulations of the universe rarely produced a void this large. Yet here it was, enveloping us. To reconcile the two, another challenge arose, understanding how this hollow space distorts everything we observe. The journey forward becomes a mission of correction. Every distance, every velocity, every expansion rate, every measurement must be untangled from the influence of the void. Light entering this underdense region accelerates across the expanding emptiness. Galaxies inside it move outward faster than expected. And the entire region grows like a bubble drifting through the cosmic web. This introduces the first major obstacle in our journey. The universe appears to expand faster here than it does elsewhere. This is not illusion, it is environmental bias. The void amplifies expansion, and the galaxies within it carry that amplification like a fingerprint. But from Earth, that fingerprint looks like a change in the laws of physics. Suddenly, the expansion rate near us does not match the expansion rate inferred from the far universe. The inconsistency becomes the first major challenge, the one now known as the Hubble tension. To understand this mismatch, the journey must continue deeper into the void, beyond the local sheet, beyond the surrounding filaments, into the heart of the underdensity where matter thins and geometry shifts. Here, expansion accelerates slightly faster than normal, as if space itself exhales more freely. This is the environment we inhabit. The task now is not just to observe it, but to understand its shape, its depth, and its influence. Every step outward clarifies the boundary between typical cosmic expansion and the enhanced expansion driven by emptiness. As you move deeper, the familiar universe fades further away. The void becomes more than a backdrop. It becomes the central challenge of the journey. The mission ahead is clear. Map the hollow, measure its distortions, untangle its effects from the true behavior of the universe. The deeper you venture, the more the void reveals itself, not as an empty region, but as a force shaping everything we believe about cosmic evolution. And this is only the beginning. As the journey continues deeper into the surrounding emptiness, the patterns in galaxy data begin to twist into something unexpected. The underdensity is no longer just a quiet backdrop. It is affecting the universe in ways that should be impossible. Distances conflict, velocities drift, and every measurement of cosmic expansion fractures into two incompatible answers. This is where tension transforms into crisis. At the edge of the local supercluster, astronomers noticed something strange. Galaxies farther out did not line up with predictions. Their redshifts were too high for their distances. The expansion seemed stronger nearby than it was in the ancient universe. The numbers refused to agree. And the deeper the surveys reached, the more the disagreement grew. The discovery was simple to describe, but difficult to accept. The universe expands at two different speeds depending on where you look. This became one of the most stubborn puzzles in modern science. The Hubble tension, the far universe, measured through the cosmic microwave background, told a clear story, a slow, steady expansion rate shaped by early conditions. But the nearby universe, the one inside the void, told a faster story, an expansion rate nearly 9% higher. Both measurements were precise, both were trusted. And yet, both could not be right. The void offered a possible answer, but not a comfortable one. Inside an underdense region, gravity loses power. With less matter to pull against expansion, galaxies drift outward more easily. This creates an illusion of an accelerated local universe. The fabric of space stretches more freely. Light travels with less gravitational interference. And the motions of galaxies pick up extra speed, not from dark energy but from the absence of mass. This was the first hint that the void might be warping our perception of the cosmos. But the tension deepened when astronomers tried to correct for this distortion. Even after adjusting for known peculiar velocities, the motions caused by gravitational pulls, something remained unbalanced. The discrepancy persisted, pointing to a deeper problem. The void is vast enough to distort even large-scale measurements. Mapping it required a new tool: barren acoustic oscillations, the frozen sound waves from the infinite universe. These waves left behind a fixed cosmic ruler across space, a distance of nearly 500 million light-years imprinted into the distribution of galaxies. But when astronomers used this ruler inside the void, they noticed a subtle mismatch. The ruler looked slightly stretched. The void had altered its apparent scale, making galaxy spacing seem wider than expected. This was the first direct proof that the void was influencing measurements across hundreds of millions of light-years. The problem grew sharper. If the void changes our perception of distances, then every measurement near us is biased. Every supernova, every galaxy redshift, every expansion calculation, even the inferred age of the universe itself. The tension was no longer just a disagreement. It was a distortion field created by our location. As maps expanded outward, another discovery raised the stakes. The deeper regions of the void showed less structure than simulations predicted. The underdensity was not simply a shallow dip. It extended for nearly 1 billion light-years in every direction. Too large, too deep, too improbable. Standard cosmology rarely produces a void of this scale. The probability of one forming by chance is vanishingly small. Yet we are clearly inside one. This realization forced cosmologists to confront a difficult possibility. Either the universe is different from what our models predict, or our models are incomplete. The tension sharpened again when the motions of distant galaxies were measured more precisely. They were flowing outward from the void interior faster than expansion alone could explain. A coherent drift across hundreds of millions of light-years. Not random, not noise. A direct gravitational signature of the void. The discovery was unmistakable. The void itself creates a large-scale velocity field, a gravitational imbalance so vast that entire regions of space move in a single direction. And the Milky Way participates in this drift, racing through space at over 600,000 miles per hour, not because space itself pulls us, but because the void behind us pushes nothing back. This was the turning point. The first technical problem, a mismatch in the Hubble constant, revealed a much deeper structure. The void was not just an emptiness in matter. It was a distortion in space-time, a region where expansion accelerates, where light experiences fewer gravitational delays, where galaxy motions reveal enormous asymmetries in the cosmic web, a region where the universe behaves differently than the models expect. The deeper the journey goes, the more the void's fingerprint appears everywhere. In expansion rates, in galaxy motions, in cosmic temperatures, in standard rulers, in every method used to decode the cosmos. What began as a small discrepancy now looks like a structural feature of space, and the next question rises, colder and more unsettling than the last. If our measurements are distorted by the void, how much of the universe have we misinterpreted? The deeper the exploration goes, the clearer the pattern becomes. The universe near us behaves differently from the universe beyond. And now, the conflict is no longer just numbers on a chart. It is a direct challenge to everything cosmology was built upon. The tension rises as observations collide with expectations. The standard model insists the universe is smooth at large scales. Yet the void around us stretches nearly 2 billion light-years across, far larger than simulations allow and far deeper than theory predicts. This inconsistency forces an uncomfortable decision. Either the universe is hiding something fundamental, or our measurements from inside the void cannot be trusted. The first signs of this deeper conflict appear when astronomers compare supernova results to cosmic microwave background predictions. The disagreement sharpens. The two expansion rates refuse to reconcile, and the void's gravitational outflow pulls harder than anticipated, accelerating galaxies outward in every direction. The data begin to reveal a disturbing truth. We are measuring the universe from inside a distortion. Galaxy velocities do not average out. Distances do not line up. The very rulers used to measure the cosmos appear stretched by the environment. The conflict becomes undeniable when the cosmic microwave background itself is examined more closely. Light from the early universe travels through the void for billions of years before reaching us. During that journey, it experiences less gravitational slowing than it should. This leaves a faint temperature imprint, a subtle cooling across the sky. Tiny, but measurable, and completely consistent with a massive void surrounding our location. Yet another contradiction emerges. The cosmic microwave background models predict a universe that is smooth at these scales. But the void observation suggests otherwise. The two views cannot coexist without tearing a hole in the foundations of cosmology. The conflict escalates further when the large-scale motion of galaxies is mapped in detail. Peculiar velocities rise far above expected levels. Entire regions drift toward denser structures with a coherence that should not exist. The flows span hundreds of millions of light years. These flows reveal a gravitational landscape that challenges everything the standard model assumes. Gravity inside the void behaves more like a slope than a uniform field. Space itself acts like a tilted plane. Galaxies slide downhill from the low-density interior toward the dense outer walls. But the slope is steeper than gravity alone should create. Something is amplifying the motion, something the models do not include. This introduces a new possibility. Either dark energy behaves differently inside voids, or gravity itself changes in low-density environments. Neither option is easy to accept. Both require a shift in physics. As the evidence builds, astronomers face a difficult choice. Should the standard model be modified? Or should they accept that our location is far from typical? Neither choice is comfortable. If the void is responsible for distorting our measurements, then the principle that no location is special collapses. Humans would once again find themselves living in a special place, not at the center of the universe, but in one of its rarest deserts. The logic is simple but troubling. If the universe is truly uniform, we should not be in such an unusual region. If we are in such a region, the universe is not uniform. Both statements cannot be true. The conflict intensifies when simulations attempt to replicate such a void. Standard cosmology struggles. The probability of producing a void of this size and depth is vanishingly small, far below what nature should allow. The numbers force another painful decision. Is the void real and the model incomplete, or are the observations biased and misleading? Each path leads into deeper uncertainty. The next wave of contradictions emerges when comparing measurements taken inside the void to those taken beyond it. Observations farther than 2 billion light-years away begin to converge toward the lower expansion rate predicted by the cosmic microwave background. This suggests a boundary, a region where the void's influence fades. Inside the bubble, the universe expands faster. Outside it, expansion slows to the global average. This creates an observational dilemma. Nearly all of humanity's most precise measurements come from within the bubble, yet the truth of the universe may lie beyond it. Every new discovery pushes astronomers toward the same question. How much of what we know depends on where we live? The conflict now threatens cosmology on multiple fronts. The expansion rate, the age of the universe, the growth of structure, the behavior of gravity, even the validity of the cosmological principle. Each piece of evidence points back toward the void. Each contradiction hints at a deeper problem, and the tension rises with every measurement. The next step in the journey will demand a decision. Should the void be accepted as the explanation for the Hubble tension, a distortion caused by our unusual location? Or should the framework of the universe itself be questioned? The laws that govern gravity, expansion, and structure. Either path leads into unfamiliar territory. Either path requires abandoning assumptions that have guided cosmology for decades. The conflict can no longer be ignored. The universe near us does not behave the same as the universe beyond, and the journey ahead will reveal just how far this discrepancy reaches. For now, we stand at the edge of a deeper mystery, a realization that the cosmic map may not match the cosmic reality. And the next chapter will show the consequences of living inside a distortion. At this stage of the journey, the evidence no longer whispers. It presses in from every direction, heavy and unavoidable. Every measurement, every map, every velocity field points toward the same unsettling reality. Our place in the universe is distorting the universe we think we see. The crisis arrives when astronomers attempt to unite all the data into a single model. A model that explains expansion. A model that explains structure. A model that does not break under the weight of the void. That model does not exist. The equations refuse to balance. The numbers resist reconciliation. The void's influence overwhelms every attempt to impose uniformity. This is the moment when the story of the universe fractures. The cosmic microwave background says one age. The nearby supernova say another. The baryon acoustic oscillations bend their ruler. The galaxy flows accelerate beyond prediction. The temperature of the universe itself dips under the shadow of emptiness. Each line of evidence alone is manageable. Together, they form a crisis unlike anything cosmology has faced in a century. The core assumption that no place in the universe is special begins to collapse. And the collapse forces a deeper reckoning. If we live in a cosmic whole, then every distance, every velocity, and every expansion measurement close to us may be biased. The sacrifice begins here. Not of people, but of ideas. Ideas once believed unshakable. One by one they fall. The first casualty is simplicity. Standard cosmology loses its clean elegance. The void demands complexity. Twisted gravitational potentials, local velocity fields, density gradients stretching across 1 billion light-years. The next casualty is certainty. No measurement made within the void can be fully trusted. Not without knowing exactly how the void distorts light and motion. Not without understanding a structure too large to measure directly. The crisis sharpens when astronomers test the universe's age. If the faster expansion inside the void were true everywhere, the universe would be younger than the oldest stars. A contradiction, a physical impossibility. It forces a heartbreaking realization. Either the stars are lying or the universe is lying, and the stars rarely lie, so the void must be changing the story. The failure moment comes when simulations attempt to rebuild the universe from its earliest conditions. They generate filaments. They generate walls. They generate typical voids. But they do not generate this, not a void this large, not a void this deep, not a void with statistical odds so small it should not appear even once in an observable cosmos. Simulation after simulation returns the same result. The structure around us is too extreme. This is when cosmologists face the most difficult possibility. If nature produces larger voids than theory predicts, then perhaps the theory itself is incomplete. Some consider modifying gravity. Others consider evolving dark energy. Still others struggle to preserve the standard model by arguing that this void, though improbable, is simply rare, and we happen to live inside it. But each option comes with a cost. Changing gravity forces a rewrite of cosmic history. Changing dark energy demands new physics. Accepting the void as chance violates the principle that we do not occupy special locations. There is no option without sacrifice. The crisis deepens when galaxies beyond the void's edge begin to reveal a different universe. A universe with a calmer expansion rate, more consistent with early cosmic measurements. The boundary appears like a faint cosmic horizon. Inside it, distortions flourish. Beyond it, order returns. The implication is unmistakable. Our local region is misleading us. This realization hits like a cold wave. If the void changes our perception of expansion, it may also distort our understanding of cosmic density, cosmic age, cosmic geometry, even the fate of the universe itself. It is here that the journey passes a point of no return. Cosmology can no longer pretend the problem will resolve itself. The contradiction will not fade. The tension will not disappear. The void will not shrink to fit the model. It stands as a silent giant. forcing physics to choose between rewriting its foundations or accepting an uncomfortable truth about our place. The crisis is not only scientific, it is philosophical. Humanity has spent centuries moving away from the center of things. Not the center of the solar system, not the center of the galaxy, not the center of the universe. Now, the void threatens that progress. It places us in a rare environment, a location that bends measurements, a position that influences every cosmic conclusion. This is the deepest conflict of all. If we are inside a distortion, can we ever know the true universe? The part ends here, in the middle of tension. In the quiet before the next revelation. In the space where old models break and new possibilities wait in the dark. Ahead lies the turning point. The moment when the void stops being a problem and becomes a clue. The crisis hangs heavily over every cosmic measurement, but it is in the quiet aftermath of conflict that a new idea begins to emerge. Not a solution. Not yet. But a shift. A way of seeing the void not as a mistake, but as a message. This is the turning point. As the data deepens, astronomers begin to realize something profound. The void may not only distort the universe, it may reveal how the universe truly works. The first hint appears in the behavior of dark energy. Inside the void, where matter is scarce, dark energy dominates with unusual clarity. It stretches space more freely. It accelerates expansion more strongly. It exposes its own properties without the interference of heavy galaxy clusters. For the first time, scientists have a clean laboratory to study the force that drives cosmic acceleration. A laboratory nearly 1 billion light-years wide. A laboratory we happen to live inside. The idea is simple but transformative. If the void magnifies the effects of dark energy, then its emptiness may not be a problem. It may be a tool. This realization changes the narrative. Instead of fighting the distortion, researchers begin to map it. Instead of ignoring peculiar velocities, they examine the flow patterns. Instead of dismissing temperature dips, they use them to trace gravitational potentials. Slowly, the void transforms from an obstacle into an X-ray window, a way to peer into the hidden forces shaping the universe. The next breakthrough comes from an unexpected direction: the shapes of voids themselves. Across the cosmic web, most voids are nearly spherical. Their boundaries expand evenly, driven by the uniform pressure of dark energy. But the KBC void has subtle irregularities, tiny distortions that reveal how mass moves within it. These distortions act like fingerprints. By studying them, astronomers can not only measure the void's growth, but also infer the strength and nature of dark energy over time. This becomes a turning point in the crisis. For the first time, a path forward appears, not through rewriting the universe, but through understanding how the void exposes the universe's hidden physics. Another shift emerges in the analysis of galaxy flows. What once appeared chaotic now reveals a pattern. Galaxies accelerate outward in a smooth gradient that reflects the void's density profile. The deeper the region, the faster the outward flow. The closer to the walls, the slower the drift. This is not random motion, it is a clock. A cosmic clock ticking in response to the gravitational imbalance. A clock whose timing encodes the void's age, depth, and origin. A clock that may help resolve the Hubble tension itself. A new plan forms. If the distortion field of the void can be mapped precisely, then the true expansion rate can be extracted from beneath it. This is no small task. It requires measuring millions of galaxies, tracking their motions across hundreds of millions of light-years, and reconstructing a gravitational landscape on unimaginable scales. But now, there is direction, there is purpose, there is hope. The turning point sharpens further when baryon acoustic oscillations reveal their own story. What once seemed like a stretched ruler becomes something more. The stretch is not uniform, it varies across the void. And that variation encodes the expansion history of our region. It means the void can now be used as a probe, a measurement tool, a cosmic lens. One that reveals how dark energy and gravity shape space differently depending on density. This insight connects all the data streams: supernova brightness, galaxy flows, cosmic temperatures, and the structure of the web itself. For the first time, the contradictions begin to align. Not disappear, but align. A pattern emerges. The universe behaves differently in regions of low density, not because physics changes, but because the environment magnifies the underlying forces. This does not erase the crisis, but it opens a path through it. The next realization is even more astonishing. Voids across the universe are not identical. Some are shallow, some are deep, some expand rapidly, some barely grow at all. By comparing these voids, astronomers can measure how dark energy acts across time and space. They can test whether it is constant or evolving, uniform or structured, simple or more complex than we imagine. What once was an emptiness now becomes a field of measurement, a place where the most mysterious force in the universe reveals itself most clearly. This is the moment the crisis begins to change shape. The void no longer threatens cosmology. It expands it. It no longer undermines the model. It strengthens its testing. It no longer hides the universe. It unveils it. Suddenly, the emptiness around us feels different. Not a flaw in nature, not a cosmic accident, but an opportunity written into the fabric of space itself. The turning point becomes clear. If the void distorts our vision, then understanding the distortion will reveal the true universe beyond it. The path ahead is still long, still uncertain, still filled with tension and unanswered questions. But for the first time, the darkness is not only a challenge, it is also a guide. And the next part of the journey will move from crisis into confrontation. A step toward the universe as it truly is, not as it appears from inside the whole. The journey through the void has revealed a structure far more complex than emptiness. A structure that shapes expansion. A structure that bends distances. A structure that challenges the foundations of cosmology. Now, the investigation reaches a rising peak. A point where evidence converges, patterns sharpen, and the universe begins to reveal its deeper machinery. This is the climb toward the climax. With new mapping tools, astronomers trace the flow of galaxies across nearly 1 billion light-years. The velocity field forms a vast, coherent pattern. Matter drains outward from the heart of the void, rolling across space like a slow cosmic tide. This tide exposes a hidden geometry, a geometry that connects everything. Galaxy clusters at the boundaries, filaments feeding larger structures, and distant attractors pulling from beyond the void's edge. The flows reveal the anatomy of a cosmic landscape, a grand slope carved into space-time by the absence of matter. The KBC void is not just a hollow. It is a gravitational basin whose shape dictates the motion of entire regions of the universe. As the map sharpens, the flows appear with uncanny clarity. They rush toward a distant gravitational peak, a massive region known as the Shapley concentration. Its enormous pull extends across hundreds of millions of light-years. The Laniakea supercluster, which includes the Milky Way, slides steadily toward it like iron filings toward a magnet. The void behind us pushes. The supercluster ahead pulls, and the entire region moves as a linked chain of drifting galaxies. This motion marks a turning point in the journey. The void does not sit in isolation. It is part of a larger, living system, a dynamic balance of attraction and emptiness, gravity and expansion. The peak approaches when cosmologists begin comparing these flows to the predictions of general relativity. The results are unsettling. The flows are too large. The void is too deep. The structures are too extreme. The coherence stretches too far. Standard gravity can explain some of this motion, but not all of it. This is where the tension reaches its steepest point. The universe appears more energetic, more dynamic, more uneven than the standard model anticipates. Observations begin to push against the limits of theory. Something must give. Either the models must bend, or the universe must be reinterpreted. The rising peak grows sharper when astronomers examine the cosmic microwave background. Tiny temperature ripples in the sky reveal a history of structure formation. But now, those ripples must pass through the void before reaching Earth. They bend, shift, and lose energy in subtle, predictable ways. This bending creates a faint but measurable shadow, a dip in temperature caused by the integrated Sachs-Wolf effect. A signature of emptiness so vast that even light from the dawn of the universe cannot cross it unchanged. This temperature shadow becomes the first cosmic imprint of the void, a mark written across the sky's oldest light. It confirms the void's presence. It confirms its scale. It confirms its influence on cosmic expansion. And it deepens the crisis. Because such a signature should be rare, unlikely, almost impossible, yet it is here, on our sky. In every direction we look, the climb continues when the rulers of baryon acoustic oscillations begin to reveal how the void stretches space unevenly. The scale of galaxy clustering shifts. Distances warp. Standard candles flicker out of expected brightness. The universe behaves differently inside emptiness. The distortion is not random. It follows a gradient, a measurable pattern, a pattern that encodes the void's true shape. Every instrument turns toward this mystery. Radio telescopes chart neutral hydrogen. Optical surveys map galaxy groups. Infrared arrays peer into hidden clusters. All paths lead to the same conclusion. The void defines our local universe. This realization builds toward the emotional peak, the moment when humanity understands its cosmic situation. We are not adrift in typical space. We are not surrounded by average density. We are not measuring a neutral universe. We live in a rare, massive, expanding hollow, a region that changes how distances appear, how velocities behave, how light travels, how the universe looks. The meaning is profound. Every cosmological model built on local measurements must be re-examined. Every assumption about expansion must be rechecked. Every derived quantity, age, size, acceleration, may carry the imprint of the void. But this is not a defeat. It is the peak before clarity. Because now, with new measurements and expanding surveys, the void becomes a map, a lens, a probe that reveals how dark energy acts in low-density regions, how gravity flows across cosmic valleys, and how the universe stitches itself together. The crisis brought uncertainty. The turning point brought direction. But this moment, this rising peak, brings understanding. The void is no longer simply emptiness. It is a structure with purpose, a tool for decoding the universe, a clue to the deeper forces shaping space itself. Ahead lies resolution, the part of the journey where meaning emerges from the tension and the dark. As the journey pushes beyond the peak, a new clarity settles over the cosmic landscape. The tension that once fractured cosmology begins to resolve, not by erasing the void's contradictions, but by accepting them and letting the evidence speak. The void no longer hides behind uncertainty. Its presence is measured, its boundaries are traced, its influence is undeniable. And now, the universe begins to show the consequences of living inside such a vast, underdense region. The first consequence emerges in the expansion rate itself. When astronomers map the Hubble constant across different distances, a pattern forms. A pattern that was once noise now becomes structure. Close to us, expansion appears fast. Farther out, expansion calms. Beyond 2 billion light-years, expansion aligns with the cosmic microwave background. The bubble becomes visible, a region where local measurements deviate, and where cosmic expansion is inflated by emptiness. This is the first major resolution. The void explains the divide between local and global expansion, but the consequences stretch farther than expansion alone. The second consequence appears in the age of the universe. Stars in the Milky Way tell a story of deep antiquity, some older than 13 billion years. Their ages make sense only if the universe is truly ancient, not younger, as the inflated expansion rate once suggested. When the void's influence is removed, the conflict dissolves. The universe regains its full age. The stars no longer contradict the cosmos. This alignment marks another step toward resolution. The void was never shortening the universe's age. It was bending our measurements toward a misleading conclusion. The third consequence emerges in galaxy motions. What once seemed like chaotic velocities now reveal a coherent acceleration outward from the underdensity. This outward drift is not random turbulence. It is the gravitational fingerprint of the void. When simulations incorporate a billion light-year depression in density, the motions line up. The flows converge toward distant attractors. The entire region moves like a vast, unbound river in space-time. This discovery resolves another long-standing conflict. Galaxies were not disobeying theory. The theory was missing the terrain beneath them. A universe shaped by valleys and slopes can no longer be measured as if it were a smooth plane. The fourth consequence emerges in the cosmic microwave background. A faint cooling, a subtle dip in temperature, is found to match the exact path taken by ancient light through the void's expanding interior. This is more than confirmation, it is a revelation. The void leaves fingerprints not only on galaxies, but on the oldest light in the universe. Even the afterglow of the Big Bang carries the scar of our cosmic environment. The fifth consequence lies in structure formation itself. Inside the void, matter gathers differently. Gravity acts with less resistance. Growth is slower. Filaments are thinner. Clusters are rarer. The cosmic web inside the void resembles an early stage of the universe, frozen in place. This helps explain the overabundance of low-mass, star-forming galaxies nearby, and the lack of rich clusters that dominate denser environments. The void becomes a model of arrested development, a region where cosmic evolution continues, but at a gentler pace. This offers a profound insight. The universe does not evolve uniformly. Different regions experience different histories. The sixth consequence points toward the future. Dark energy accelerates expansion fastest, where matter is scarcest. Voids are the first places to feel this acceleration fully. The first regions where cosmic separation begins. In distant epochs, the KBC void will expand faster than its surroundings, stretching its boundaries, deepening its emptiness, and isolating its inner galaxies from the wider cosmic web. The future of our region becomes clear. The void will grow, and everything inside it will drift farther from the universe beyond. This leads to a profound realization. We inhabit a region that will one day fall silent. For now, galaxies remain visible, their light crossing billions of years to reach us. But as expansion accelerates, many of those galaxies will fade beyond the cosmic horizon. The void is not simply an environment, it is a fate. The seventh consequence emerges from a deeper philosophical point. If we live in an underdense region, then our cosmic perspective is unique, not privileged, not central, but shaped by circumstances rare on cosmic scales. This challenges the assumption that all observers see the same universe. They do not. Their environment shapes their observations, just as ours shapes ours. This insight resolves one final contradiction. The Hubble tension was never simply a numerical disagreement. It was evidence that the universe cannot be interpreted as if every location is identical. Now, at the end of the resolution phase, the consequences stand clear. The void inflates our measurements. It shifts our perception of cosmic history. It bends the path of ancient light. It guides the motion of entire galaxy groups. It shapes the structure of the cosmic web. It predicts the future of our region. It challenges the universality of perspective, and it brings unity to the contradictions that once fractured cosmology. With the crisis understood and the turning point behind us, the journey prepares to step into meaning, the emotional conclusion that reveals what this cosmic hollow truly signifies. As the journey pushes beyond the peak, a new clarity settles over the cosmic landscape. The tension that once fractured cosmology begins to resolve, not by erasing the void's contradictions, but by accepting them and letting the evidence speak. The void no longer hides behind uncertainty. Its presence is measured, its boundaries are traced, its influence is undeniable. And now, the universe begins to show the consequences of living inside such a vast, underdense region. The first consequence emerges in the expansion rate itself. When astronomers map the Hubble constant across different distances, a pattern forms. A pattern that was once noise now becomes structure. Close to us, expansion appears fast. Farther out, expansion calms. Beyond 2 billion light-years, expansion aligns with the cosmic microwave background. The bubble becomes visible, a region where local measurements deviate, and where cosmic expansion is inflated by emptiness. This is the first major resolution. The void explains the divide between local and global expansion, but the consequences stretch farther than expansion alone. The second consequence appears in the age of the universe. Stars in the Milky Way tell a story of deep antiquity, some older than 13 billion years. Their ages make sense only if the universe is truly ancient, not younger, as the inflated expansion rate once suggested. When the void's influence is removed, the conflict dissolves, the universe regains its full age. The stars no longer contradict the cosmos. This alignment marks another step toward resolution. The void was never shortening the universe's age. It was bending our measurements toward a misleading conclusion. The third consequence emerges in galaxy motions. What once seemed like chaotic velocities now reveal a coherent acceleration outward from the underdensity. This outward drift is not random turbulence. It is the gravitational fingerprint of the void. When simulations incorporate a billion light-year depression in density, the motions line up. The flows converge toward distant attractors. The entire region moves like a vast, unbound river in space-time. This discovery resolves another long-standing conflict. Galaxies were not disobeying theory. The theory was missing the terrain beneath them. A universe shaped by valleys and slopes can no longer be measured as if it were a smooth plane. The fourth consequence emerges in the cosmic microwave background. A faint cooling, a subtle dip in temperature, is found to match the exact path taken by ancient light through the void's expanding interior. This is more than confirmation, it is a revelation. The void leaves fingerprints not only on galaxies, but on the oldest light in the universe. Even the afterglow of the Big Bang carries the scar of our cosmic environment. The fifth consequence lies in structure formation itself. Inside the void, matter gathers differently. Gravity acts with less resistance. Growth is slower. Filaments are thinner. Clusters are rarer. The cosmic web inside the void resembles an early stage of the universe, frozen in place. This helps explain the overabundance of low-mass, star-forming galaxies nearby, and the lack of rich clusters that dominate denser environments. The void becomes a model of arrested development, a region where cosmic evolution continues, but at a gentler pace. This offers a profound insight. The universe does not evolve uniformly. Different regions experience different histories. The sixth consequence points toward the future. Dark energy accelerates expansion fastest where matter is scarcest. Voids are the first places to feel this acceleration fully, the first regions where cosmic separation begins. In distant epochs, the KBC void will expand faster than its surroundings, stretching its boundaries, deepening its emptiness, and isolating its inner galaxies from the wider cosmic web. The future of our region becomes clear. the void will grow, and everything inside it will drift farther from the universe beyond. This leads to a profound realization. We inhabit a region that will one day fall silent. For now, galaxies remain visible, their light crossing billions of years to reach us. But as expansion accelerates, many of those galaxies will fade beyond the cosmic horizon. The void is not simply an environment, it is a fate. The seventh consequence emerges from a deeper philosophical point. If we live in an underdense region, then our cosmic perspective is unique, not privileged, not central, but shaped by circumstances rare on cosmic scales. This challenges the assumption that all observers see the same universe. They do not. Their environment shapes their observations, just as ours shapes ours. This insight resolves one final contradiction. The Hubble tension was never simply a numerical disagreement. It was evidence that the universe cannot be interpreted as if every location is identical. Now, at the end of the resolution phase, the consequences stand clear. The void inflates our measurements. It shifts our perception of cosmic history. It bends the path of ancient light. It guides the motion of entire galaxy groups. It shapes the structure of the cosmic web. It predicts the future of our region. It challenges the universality of perspective, and it brings unity to the contradictions that once fractured cosmology. With the crisis understood and the turning point behind us, the journey prepares to step into meaning, the emotional conclusion that reveals what this cosmic hollow truly signifies. As the journey pushes beyond the peak, a new clarity settles over the cosmic landscape. The tension that once fractured cosmology begins to resolve, not by erasing the void's contradictions, but by accepting them and letting the evidence speak. The void no longer hides behind uncertainty. Its presence is measured, its boundaries are traced, its influence is undeniable. And now the universe begins to show the consequences of living inside such a vast, underdense region. The first consequence emerges in the expansion rate itself. When astronomers map the Hubble constant across different distances, a pattern forms. A pattern that was once noise now becomes structure. Close to us, expansion appears fast. Farther out, expansion calms. Beyond 2 billion light-years, expansion aligns with the cosmic microwave background. The bubble becomes visible, a region where local measurements deviate, and where cosmic expansion is inflated by emptiness. This is the first major resolution. The void explains the divide between local and global expansion, but the consequences stretch farther than expansion alone. The second consequence appears in the age of the universe. Stars in the Milky Way tell a story of deep antiquity, some older than 13 billion years. Their ages make sense only if the universe is truly ancient, not younger, as the inflated expansion rate once suggested. When the void's influence is removed, the conflict dissolves. The universe regains its full age. The stars no longer contradict the cosmos. This alignment marks another step toward resolution. The void was never shortening the universe's age. It was bending our measurements toward a misleading conclusion. The third consequence emerges in galaxy motions. What once seemed like chaotic velocities now reveal a coherent acceleration outward from the underdensity. This outward drift is not random turbulence. It is the gravitational fingerprint of the void. When simulations incorporate a billion light-year depression in density, the motions line up. The flows converge toward distant attractors. The entire region moves like a vast, unbound river in space-time. This discovery resolves another long-standing conflict. Galaxies were not disobeying theory. The theory was missing the terrain beneath them. A universe shaped by valleys and slopes can no longer be measured as if it were a smooth plane. The fourth consequence emerges in the cosmic microwave background. A faint cooling, a subtle dip in temperature, is found to match the exact path taken by ancient light through the void's expanding interior. This is more than confirmation. It is a revelation. The void leaves fingerprints not only on galaxies, but on the oldest light in the universe. Even the afterglow of the Big Bang carries the scar of our cosmic environment. The fifth consequence lies in structure formation itself. Inside the void, matter gathers differently. Gravity acts with less resistance. Growth is slower. Filaments are thinner. Clusters are rarer. The cosmic web inside the void resembles an early stage of the universe, frozen in place. This helps explain the overabundance of low-mass, star-forming galaxies nearby, and the lack of rich clusters that dominate denser environments. The void becomes a model of arrested development, a region where cosmic evolution continues, but at a gentler pace. This offers a profound insight. The universe does not evolve uniformly. Different regions experience different histories. The sixth consequence points toward the future. Dark energy accelerates expansion fastest, where matter is scarcest. Voids are the first places to feel this acceleration fully, the first regions where cosmic separation begins. In distant epochs, the KBC void will expand faster than its surroundings, stretching its boundaries, deepening its emptiness, and isolating its inner galaxies from the wider cosmic web. The future of our region becomes clear. The void will grow, and everything inside it will drift farther from the universe beyond. This leads to a profound realization. We inhabit a region that will one day fall silent. For now, galaxies remain visible, their light crossing billions of years to reach us. But as expansion accelerates, many of those galaxies will fade beyond the cosmic horizon. The void is not simply an environment, it is a fate. The seventh consequence emerges from a deeper philosophical point. If we live in an underdense region, then our cosmic perspective is unique, not privileged, not central, but shaped by circumstances rare on cosmic scales. This challenges the assumption that all observers see the same universe. They do not. Their environment shapes their observations, just as ours shapes ours. This insight resolves one final contradiction. The Hubble tension was never simply a numerical disagreement. It was evidence that the universe cannot be interpreted as if every location is identical. Now, at the end of the resolution phase, the consequences stand clear. The void inflates our measurements. It shifts our perception of cosmic history. It bends the path of ancient light. It guides the motion of entire galaxy groups. It shapes the structure of the cosmic web. It predicts the future of our region. It challenges the universality of perspective, and it brings unity to the contradictions that once fractured cosmology. With the crisis understood and the turning point behind us, the journey prepares to step into meaning, the emotional conclusion that reveals what this cosmic hollow truly signifies. In the quiet that follows resolution, a deeper question rises. Not a question about measurements or expansion or cosmic structure, but a question about meaning, about place, about legacy. What does it truly mean to live inside a cosmic void? For centuries, humanity has pushed against the idea of being central. We learned we were not at the center of the solar system, not at the center of the galaxy, not at the center of the universe. Each revelation moved us outward, toward humility, toward cosmic understanding. But the void brings a new kind of perspective, a realization not of centrality, but of rarity. We are not in an average place. We are not in a typical region of space. We live inside a bubble of underdensity, stretching nearly 2 billion light-years across, a hollow carved into the cosmic web, where galaxies are fewer, clusters are sparse, and the fabric of space expands more freely. This environment shapes everything we observe. It bends the path of light. It shifts the rhythm of cosmic time. It sculpts the motion of galaxies. It sets our local expansion apart from the global one. It gives us a universe that looks different from the universe beyond. And yet, somehow, this place became our home. The emotional weight of this realization grows when we consider the quietness of our cosmic neighborhood. Here, Galaxies interact less violently than in dense clusters. Here, star formation moves at a gentler pace. Here, catastrophic events like nearby supernovae and gamma-ray bursts occur less frequently. Here, chemical enrichment unfolds over billions of years, leaving worlds like Earth time to assemble complexity. The void may not have created life, but it created the conditions for life to endure. This is the first deep meaning of our location. Emptiness can be protective, silence can be fertile, isolation can be stabilizing. In a universe shaped by violence and collapse, the void is a refuge. The second meaning emerges from perspective. Civilizations living in dense clusters would see a universe overflowing with galaxies, glowing with X-ray halos, crowded with structure. Their sky would be a tapestry of brilliance. Ours is not. Our night sky is sparse. Our nearest galaxies are distant islands. Space feels wide, open, unhurried. To us, this is normal, but it is not universal. Our cosmic environment has shaped our sense of scale, our interpretation of space, our understanding of the universe's structure. Without knowing it, we built our cosmology inside a special pocket, one that makes expansion appear faster, one that distorts distances, one that bends the rules just enough to challenge every model we create. This is the second meaning. Our observations are shaped by where we live. Our perspective is local, not absolute. The third meaning arrives when we consider the future. As dark energy continues to accelerate expansion, the void will grow, its walls will stretch apart, nearby galaxies will drift beyond visibility. Even the light we see today will eventually fade into wavelengths too long to detect. In time, our region of space will fall silent. Not metaphorically, literally. The cosmic microwave background will dim into nothingness. Distant clusters will disappear beyond the horizon. The universe outside the void will become unreachable. Future civilizations living in this quiet bubble may never discover cosmology as we know it. Their sky will offer no clues of a larger universe. They will live inside a single island of stars, unable to see the story that unfolded before them. This is the third meaning. We are living in a rare moment, a window of cosmic history, when the universe is still visible. We are early enough to see beyond the void, yet late enough to trace its shape. We exist at the intersection of revelation and retreat, a narrow era when the cosmos still speaks, and emptiness has not yet silenced the sky. The fourth meaning emerges from wonder. If the void is rare, other civilizations may be rare too. Isolated galaxies may foster long-term stability, but they also limit the opportunities for life to spread. We might not only be unusual in location, we might be unusual in existence. The void forces us to confront the possibility that life itself may be shaped by the cosmic environment, by density, by silence, by the rhythm of star formation, by the pace of cosmic evolution. This leads toward the deepest meaning of all. We are products of a universe that is uneven, structured, layered, and astonishingly complex. The void does not diminish that complexity. It reveals it. Our place inside this underdense expanse is a reminder that the universe is not uniform, it is textured, it is varied. It contains extremes, vast clusters of blazing galaxies, and immense hollows of quiet darkness. And in that mixture, we found ourselves, not at the center, not at a privileged point, but in a rare environment that shaped our sky, our science, and our understanding. In the grand cosmic landscape, our void is both a challenge and a gift, a distortion and a discovery, a problem for cosmology, and a key to unlocking its deepest truths. As the emotional conclusion settles, the legacy of this journey becomes clear. To live inside a cosmic hole is not to be lost. It is to be positioned where the universe reveals itself through emptiness, where silence carries information, where scarcity becomes a lens, where the shape of nothing teaches the meaning of everything. What lies beyond the void is not emptiness, but revelation. The next stage of the journey turns outward, away from the hollow that surrounds us, and toward the vast structures that define the rest of the universe. The walls of the void lead into filaments thicker than any we have crossed so far. Rivers of galaxies stretch into the distance, merging into clusters so dense they reshape the fabric of space itself. Ahead, the cosmic web becomes sharper, richer, and more complex. The coming exploration shifts focus from the underdense basin we inhabit to the immense structures that surround it. These structures, built from hundreds of thousands of galaxies, anchor the universe with gravity strong enough to sculpt entire regions of space. The journey moves from silence into motion, from emptiness into the crowded highways of the cosmos. The first view will be the boundary of the void, the region where galaxy density rises sharply, where filaments reconnect, and where gravitational forces become stronger than anything found inside the hollow. This boundary is not a wall but a transition zone, a cosmic shoreline, where emptiness meets structure. Understanding this region will reveal how gravity organizes matter across billions of light years. Beyond it lies the Laniakea supercluster's outer flow lines. These lines show how galaxies drift across vast distances, following the pull of larger masses. They are not random paths, but ordered streams that point toward one of the most influential regions in the nearby universe, the Shapley concentration. This colossal assembly of galaxies is so massive that it bends motion across hundreds of millions of light years. As the story continues, the journey will trace these flows outward. The path will reveal how entire superclusters move like currents in a cosmic ocean, how local structures respond to distant attractors, and how the void itself contributes to these motions by reducing resistance to expansion. The next phase will explore how different regions of the universe evolve under different conditions. Dense clusters ignite with energetic activity, starbursts, mergers, collisions, and powerful radiation. The journey ahead will compare these dramatic environments with the quiet, slow-forming galaxies of the void. This contrast reveals how environment shapes cosmic destiny, influencing star formation, galaxy evolution, and the chemical ingredients of worlds. The upcoming exploration also turns toward the universe's early history. Beyond the void's boundaries, the imprint of baryon acoustic oscillations becomes clearer and more precise. These frozen sound waves from the young universe act as a ruler for cosmic expansion. By stepping outside the void's distortion field, the journey will examine how this ruler behaves in typical regions, offering a cleaner measurement of cosmic history. Farther ahead lies a deeper question. How does the cosmic landscape change across time? Not just across space, but across billions of years of evolution. The continuation will follow the growth of structure from the earliest galaxies to the present day. It will show how filaments thickened, how voids expanded, how clusters assembled, and how dark energy influenced each phase. It will explore whether the large-scale universe we see today is stable, evolving, or drifting toward a future dominated entirely by emptiness. In the next stage, the investigation will widen its scope to the largest cosmic maps ever made, surveys that chart tens of millions of galaxies across nearly the entire sky. These maps reveal patterns far beyond human perception, waves of density, stretches of emptiness, and threads of matter that span hundreds of millions of light years. The journey ahead will explain how these maps are made, how light from distant galaxies carries the history of cosmic expansion, and how these observations help determine whether the void around us is typical, rare, or part of a greater pattern. The next exploration also turns toward the deepest cosmic signal, the cosmic microwave background. By looking beyond the void, the journey will show how the temperature of the early universe connects to large-scale structure today. It will reveal what remains unexplained, what is confirmed, and what still challenges the boundaries of physics. Along the way, the story will follow the universe's most ancient photons as they cross billions of light years, slipping through clusters, filaments, and voids. Their journey reveals how gravity warps space, how dark energy stretches it, and how the cosmic landscape has changed since the dawn of time. The next chapters will explore these transformations. They will trace how the cosmic web formed from tiny quantum ripples, how it stretched into the structures we see today, and how it will evolve into the distant future. The continuation moves toward the universe's ultimate fate. It will examine how accelerating expansion gradually pulls galaxies apart, how superclusters fragment into isolated islands, and how the cosmos may drift toward a future ruled entirely by emptiness. This future is not a collapse, but a quiet drift toward solitude. A universe where regions like the one we inhabit become the norm, each isolated by distances no light can cross. The coming story will reveal how long this transformation will take, how it will reshape the cosmic web, and how it will determine what future civilizations can see, study, or understand. The next exploration will widen the view to life itself. It will ask how the cosmic environment, dense or empty, influences the potential for stars, planets, and complex chemistry. It will consider whether the quiet nature of void galaxies helps or hinders the rise of life, and what this means for our own existence. In the chapters ahead, the journey becomes not just an explanation of cosmic structure, but a meditation on what it means for civilizations to grow in different cosmic environments. The story will ask whether life in crowded galaxy clusters faces more danger, and whether life in voids evolves differently. Finally, the continuation will look outward into regions of the universe untouched by the KBC void. It will reveal how the cosmos behaves beyond our distortion field, how far the void's influence reaches, and what lies outside the bubble that shaped every cosmic measurement we have ever made. The preview ends with a simple truth. The void is not the whole universe. It is only the beginning of the universe we are about to explore. The journey through the void uncovers more than structure and expansion. It reveals quiet truths hidden inside the fabric of space. Truths that deepen the mystery of our cosmic home. These are not theories or speculations, but measurable features of the universe. Yes, one of the most surprising facts is that voids dominate the universe. Even though galaxies glow brightly and clusters hold immense mass, not. More than half of the universe's volume consists of vast hollows, places where matter is sparse, where gravity weakens, and where dark energy gains strength. The KBC void is one of the largest of these regions, but it is not alone. It is part of a pattern, a cellular network of empty bubbles separated by thin walls of galaxies. Another remarkable fact is how these voids formed. They did not appear suddenly, they grew. In the early universe, slight variations in density created tiny seeds. Dense areas became clusters and filaments. Underdense areas expanded faster, slowly hollowing out into enormous basins. Over billions of years, these basins merged, deepened, and stretched into voids that can now span hundreds of millions of light years. The KBC void is one such basin, a layered cavity shaped by time, expansion, and gravity. Its size is extreme, but its origin follows the same ancient rule. Dense regions collapse inward, while empty regions stretch outward. A striking fact is how this shape affects the speed of expansion. Inside a void, space stretches more quickly because there is less matter to slow expansion through gravity. This allows the void to mimic the effects of dark energy. It creates a slightly faster expansion rate that can be mistaken for a fundamental difference in the universe itself. This is why living inside a void complicates measurements. The environment amplifies the appearance of acceleration. Another hidden truth lies in the temperature of the universe. The cosmic microwave background is nearly uniform, yet its faint ripples carry evidence of every major structure light has crossed on its way to us. When that ancient light passes through a void, it experiences less gravitational slowing and ends up slightly cooler upon arrival. This temperature drop is tiny, only millionths of a degree, but detectable with precise instruments. It is one of the clearest signatures that we are surrounded by an underdense region. A further revelation is how deeply voids influence galaxy motion. Galaxies inside voids are not simply drifting randomly. They flow. They follow structured paths that respond to the void's shape. Inside the KBC hollow, these flows move outward, as if the entire region is breathing gently into space. Near the edges, galaxies turn toward dense filaments, falling into superclusters and larger attractors. These motions create a cosmic gradient that reveals where the void begins, where it ends, and how it sculpts space. Another fascinating fact involves galaxy evolution. Galaxies inside voids are some of the most pristine in the universe. They evolve slowly because interactions are rare. They retain their gas longer. They form stars at a steady pace. They remain blue, youthful, and chemically simple. In dense regions, galaxies collide and merge, burn through their gas, and grow older more quickly. Void galaxies avoid this hectic life. They drift in quiet isolation, forming stars for billions of years, at a calm and uninterrupted rate. This makes voids important laboratories for understanding how galaxies behaved in the early universe. Some void galaxies resemble ancient galaxies, frozen in time. Simple disks of gas and stars that change only gradually. Another profound fact is that the void affects not only matter, but the perception of space itself. Distances measured inside a void stretch subtly. Light bends differently. Rulers made from cosmic patterns, like baryon acoustic oscillations, appear slightly larger than they should. These small shifts accumulate and become part of the Hubble tension, a sign that our location influences what we measure. Another remarkable aspect is how rare our region seems to be. Simulations based on standard cosmology can reproduce voids of many sizes, but voids as large and deep as the KBC region are uncommon. Their formation requires unusual conditions, which raises questions about how typical our cosmic home truly is. If voids like this are rare, our location becomes statistically unusual, a contrast to the long tradition in science that places humanity in non-special positions. Another fact touches the future. The void is expanding, not just in the sense of cosmic expansion, but in the sense that its interior grows emptier over time. Galaxies near the edges drift outward, filaments thin, clusters retreat. In billions of years, the void will be larger, darker, and more isolated than it is now. The universe's long-term evolution is a journey toward increasing emptiness, with voids swallowing more and more of the cosmic web. This leads to another sobering truth. As expansion accelerates, light from distant galaxies will no longer reach us. The horizon will shrink. The universe will appear emptier, not because matter disappears, but because distance expands faster than light can cross it. The cosmic web will seem to fade, even as it continues to exist beyond reach. Void dwellers of the far future may live in a world without visible galaxies, without cosmic history, without clues to the universe's beginnings. Their sky will hold only the stars of their local group. The larger universe will be hidden behind an expanding curtain of space. And yet, even in this distant fate, there is awe, because the universe, through its structure, reveals that emptiness is not absence, it is architecture. It is influence. It is a silent force that shapes the largest patterns in existence. Void regions are not failures of structure. They are part of the structure. They help define where galaxies form, how they move, how they evolve, and how the universe grows. The more we learn about our hollow cosmic home, the more we understand a deeper truth. The universe is not uniform. It is a grand landscape of peaks and basins, clusters and voids, gravity and dark energy, woven together into a vast, living web. Inside this web, our region of emptiness is not an error, it is a chapter, one that adds complexity, mystery, and meaning to the story of the universe. The journey through this vast cosmic hollow now reaches its end. We began at the edge of a mystery, a discovery so large, so quiet, and so unexpected. Tweeny, we learned that our home is not set in an ordinary region of space. We drift inside a desert of matter, stretching nearly 2 billion light-years across. And where dark energy reveals its true strength. This void is not a simple, empty region. It is a structure formed over billions of years. To give. It expands, it shapes, it influences. It bends the path of light, and from our tiny place within it. We saw how the void affects the Hubble tension, how it can make the universe appear to expand faster here than it does elsewhere. For this, we explored the cosmic web, a network of filaments and clusters, and we learned that this web is surrounded, stitched together, and shaped by emptiness. We discovered how voids reveal dark energy by exposing the universe's accelerated expansion in its purest form. Gravity, and we traveled through time, seeing how small ripples in the early universe grew into the peaks and valleys we observe today. And we followed those patterns forward into a distant future where isolation becomes the universe's final state. We saw how galaxies inside voids live different lives, quiet lives, slow lives, that we, leaving behind only scattered islands of stars. We witnessed how the void challenges the cosmological principle, pressing us to ask whether our place is ordinary or whether we live in a truly unusual region, a place that biases our observations, shapes and colors our understanding of the universe. And through all of this, one truth remained clear. The universe is far stranger and far more beautiful than the smooth, simple picture we once imagined. It is a universe of contrast, light and dark, and structure and silence, a universe built by gravity and driven apart by dark energy. Still, where perspective shapes truth, where even emptiness has power. Standing at the end of this journey, we can see that the void is not a flaw in the cosmos or an accident of structure. It is a defining feature of the universe's architecture. It is not uniform, not simple, and not easily understood from a single point of view. It reminds us that every measurement we make begins from this hollow region, a region that stretches our understanding. And it warns us that the cosmos may be hiding the full picture from us, not out of deception, but because of the limits of our vantage point. And it invites us to continue searching, to look farther, to measure deeper, to question every assumption we inherit. Because the universe does not reveal itself all at once. It reveals itself piece by piece, layer by layer, void by void, and each discovery reshapes the story. As this documentary comes to a close, the journey does not end. It extends into your curiosity, them, those, and of this vast cosmic hollow. We are wanderers inside a great emptiness, not lost, but learning, not isolated, but connected to the deepest forces that shape the universe. The void is not a boundary. It is a beginning, a reminder that the unknown is still immense, and that our place within it, toward understanding the universe as it truly is. The deeper we look into the structure of the universe, the clearer one truth becomes. Every part of the cosmos depends on perspective. What we call empty may hold meaning, in, and may not reflect the universe as a whole. Inside this vast hollow, our measurements stretch and shift, like reflections on a rippled surface. Distances change, velocities distort, But these distortions are not errors, they are signatures. They tell us that the universe is textured, layered, and full of hidden depth. The cosmic void is not a blank space. It is a lens. It shapes what we see. And when astronomers map the universe, they rely on light that has traveled for billions of years. Every photon carries a story of the space it crossed. Every wavelength holds a memory. From our vantage point inside the void, these signals arrive, altered in gentle ways. Not enough to deceive, but if we assume the universe is smooth and uniform. The more we study this region, the more we see how measurement itself is shaped by environment. In dense regions, gravity slows the expansion of space. Inside voids, this difference alone can shift the expansion rate we observe. It is a reminder that the universe is not a single story. It is woven across billions of light years. Our story begins inside a hollow, but it does not end there. As we map the outer edges of the void, we find the surrounding filaments, the walls of this cosmic cavern. They glow with clusters and superclusters, places where matter has gathered in. These walls are not solid, they are porous, shifting. Matter flows along them like rivers of starlight, guiding galaxies toward deeper gravitational sinks, far beyond our reach. From the void's center, the universe appears smooth, as if distributed evenly. But this is an illusion, created by distance. In truth, the cosmic web is a vast, uneven structure. Great walls rise in the distance. Gigantic clusters anchor intersections. And between every filament lies a hollow, each shaped by the same ancient forces that shaped our own. The KBC void is one chapter in a much larger cosmic architecture. It sits among other giant hollows, some nearby, some far away, all contributing to the universe's grand design. As we explore this architecture, one question grows louder. What does it mean to be typical in a universe of extremes? Perhaps typical does not exist. Perhaps there are only local realities, each shaped by its environment, each revealing a different truth about how the cosmos evolves. From inside a void, we see a universe where expansion appears faster, where light travels farther, with less interference, and where the structure around us seems to thin out, as if space itself breathes in slow, quiet motions. From within a dense cluster, the universe would look different, crowded, active, driven by collisions and gravity, strong enough to reshape galaxies. Both perspectives are real. Both perspectives are valid. They are simply different windows into the same cosmic whole. The more we understand this, the clearer our place becomes. Not unique, not central, not privileged. Just one viewpoint among countless possibilities. But this viewpoint comes with a rare opportunity. By studying the void, we learn how dark energy behaves when gravity retreats. We learn how galaxies grow when left alone for billions of years. We learn how cosmic expansion changes across environments. Most importantly, we learn that the universe is far more dynamic than uniform models suggest. Every filament, every cluster, every empty gulf adds a new layer to the story of the cosmos. Even the void beneath us, quiet, vast, and almost invisible, plays a crucial role in shaping the expansion of space and the motions of galaxies. As we look outward from this hollow, we are reminded that the universe is not a flat map, but a living structure, still forming, still stretching, still evolving. The emptiness around us is not a mistake. It is part of the design, a balancing force that allows the cosmic web to exist. In the early universe, tiny fluctuations created differences that gravity later amplified. Those differences became the architecture of everything. The voids did not fail to form galaxies. They succeeded at becoming exactly what cosmic evolution shaped them to be. Vast expanses where matter drained away, leaving behind quiet galaxies, suspended in darkness. Now, billions of years later, these voids remain as silent witnesses to the universe's past, and we, floating inside one, interpret the cosmos through their lens. Our measurements reflect their influence. Our models contend with their presence. Our questions grow larger because of their scale. This is not a limitation. This is a gift. Every challenge the void presents pushes science deeper. Every tension it creates forces theory to evolve. Every measurement it distorts reveals a new piece of truth. We are not observers trapped in emptiness. We are explorers stationed at the edge of one of the universe's greatest laboratories, a place where cosmic forces unfold in their purest form. Here, in this enormous hollow, we learn what the universe truly is. And we learn that our place within it is part of the story, not an exception to it. Beyond the horizon of our vast hollow, the universe grows richer and more crowded. The KBC void is enormous, but it is not the whole story. Its edges give way to a busier cosmos where filaments thicken and clusters rise like mountain ranges made of galaxies. Step outward in thought, and the scene changes. The faint glow of distant structure brightens. Long threads of matter sharpen into filaments. Galaxies appear more numerous, their shapes become varied. Collisions increase. Gravity sculpts dramatic arcs of gas and stars. The restless activity of dense regions contrasts with the quiet inside the hollow. The walls of the void are not solid barriers. They are gradual transitions in density, regions where gravity has gathered matter over billions of years. Crossing these boundaries is like watching a blurred image come into focus. The space that looked empty at first now resolves into a rich network of galaxies linked by threads of dark matter. Here, in the crowded zones, galaxy clusters dominate. These are vast gatherings of hundreds or thousands of galaxies bound by gravity and dark matter. Hot plasma fills the space between their member galaxies and shines in X-rays. At their centers, supermassive black holes blaze, launching jets that shape the surrounding gas. Clusters sit at the intersections of filaments, collecting matter that flows along cosmic highways. The structures beyond the void are the engines of cosmic change. Galaxies fall into clusters, merge, and trigger bursts of star formation. Gas is stripped and heated. Black holes grow by swallowing gas and stars. These processes drive rapid evolution in ways that seldom occur inside voids. The universe outside the hollow is dynamic and full of transformation. Among the largest features are superclusters and great walls, the vast, coherent structures that stretch for hundreds of millions of light years. Names like Shapley, Laniakea, and the Sloan Great Wall mark places where gravity has been especially successful at concentrating matter. From the center of our void, these structures may look like distant beacons. Up close, they are landscapes of endless activity and complexity. Dark energy acts everywhere, but its effects play out differently depending on the local environment. In dense regions, gravity fights dark energy's push and slows local expansion. Filaments and clusters resist, drifting apart. In voids, dark energy faces less resistance and expansion proceeds more freely. This contrast means that the future of the universe will look different in different places. Dense regions may remain bound for a long time, while voids expand and isolate their contents more quickly. The universe beyond the void teaches us about time as well as space. Dense regions show the accumulated history of structure formation. They record billions of years of mergers and growth. When we study clusters and filaments, we read a chronicle of how gravity transformed the early density ripples of the universe into the architecture we see today. Mapping this outer cosmos requires many wavelengths of light. Optical telescopes reveal galaxy shapes and colors. Radio arrays trace reservoirs of cold gas. X-ray observatories detect the hot plasma in clusters. Infrared instruments uncover dusty, star-forming regions hidden from visible light. Together, these views build a layered picture of how matter assembles on the largest scales. Peculiar velocities in these regions are complex. Galaxies move under the combined influence of expansion and local gravity. Flows converge toward dense nodes, producing streaming motions that can reach many hundreds of kilometers per second. These motions carry information about the distribution of unseen dark matter and the strength of gravitational wells across space. The interplay between voids and clusters also explains why the cosmic web is self-similar at different scales. Tiny density fluctuations in the early universe grew into sheet-like walls and filamentary highways. Over time, small clumps merged into larger structures. The same physics acts over vast ranges of size, producing a cosmic architecture that repeats patterns across scales. Studying regions beyond our void helps calibrate the cosmic rulers we use to measure the universe. Baryon acoustic oscillations, the frozen sound waves from the early universe, appear with consistent scale in typical regions. By comparing measurements inside and outside the void, astronomers can separate local distortions from the true cosmic expansion history. This comparison is essential to resolving tensions in the measured Hubble constant. The universe beyond the void also offers clues to extreme phenomena. Rich clusters host rare events, powerful radio galaxies, massive galaxy collisions, and intense starbursts. These processes enrich the intergalactic medium with heavy elements, seeding future generations of stars and planets. Observing such environments reveals how chemistry evolves on a cosmic scale. Looking outward, we also confront the cosmic future. Dark energy will continue to stretch space. Over billions and trillions of years, regions that are not gravitationally bound will recede beyond each other's horizons. Superclusters that now hold together may fragment into isolated islands. Even the busiest parts of the universe will eventually experience an era of increasing solitude. Yet the differences between environments mean that this fate will not be uniform. Dense clusters may remain bound and visible to their inhabitants for longer, while voids will empty and cool more rapidly. The universe's diversity today will translate into a varied future. Islands of light, surrounded by ever-expanding darkness. The view beyond the void reminds us that our local perspective is partial but powerful. By stepping outside our hollow mentally and observationally, we can see how the cosmic web organizes itself and how forces like gravity and dark energy govern that organization. We learn that the universe is a tapestry of extremes, and that understanding both empty and crowded regions is crucial for a complete picture. The universe beyond the void is not a different cosmos. It is the same cosmos viewed from another place on the grand stage. The laws of physics hold, but their outcomes vary with environment. The cosmic web balances emptiness and concentration, creating a universe that grows more complex over time and more isolated in the distant future. To understand the whole, we must study both the hollow and the hills that surround it. Only then can we read the story written across space and time, a story of growth, drift, collision, and quietude. The architecture beyond our void shows us what matter becomes when gravity is given free rein. and it reveals the full complexity of the universe we inhabit. Living inside a cosmic void does more than shift numbers on a chart. It alters how we see the universe, how we measure time, how we understand distance, and even how we imagine our own origins. A void this large is not just an empty space, it is a silent influence, a force that shapes every observation we make without ever revealing itself directly. Inside this hollow, the fabric of the universe behaves differently. Expansion moves a little faster, gravity feels a little weaker, distances stretch a little more easily, light crosses more smoothly through the thin matter around us. Every signal we receive from the cosmos passes through this environment first. Every measurement begins with this bias. Every conclusion depends on how well we account for it. This subtle distortion echoes through all of cosmology. It affects the inferred size of the universe. It affects the measured rate of expansion. It touches the age of ancient stars and the temperature pattern of the cosmic microwave background. These effects, though small individually, stack together into the tensions and mysteries that define modern astronomy. Even the structure of the Milky Way carries traces of the void's influence. Galaxies in underdense regions evolve quietly. They merge less often. Their gas is not stripped by crowded environments. Their rotation stays smooth and undisturbed. Our galaxy's calm history, its long, stable disk, its steady star formation, its gentle environment, reflects the slow evolutionary pace inside voids. Had the Milky Way formed in a dense region, its story might have been different. More collisions, more violent mergers, more disruption, perhaps fewer stable planetary systems like ours. The void shaped our environment long before we ever realized it existed. It also shapes the large-scale flows of galaxies around us. Matter drains out of voids over billions of years, moving toward the surrounding filaments and clusters. This creates the outward streaming motion seen in bulk flow maps. These motions reveal subtle pressure exerted by the hollow itself, a gentle push, caused not by matter, but by its absence. Such flows give the KBC void its boundaries. They reveal where the underdensity fades and where the universe returns to its average richness. Inside these boundaries, galaxies drift slowly outward. Outside them, galaxies fall toward dense attractors, like Shapley and Virgo. This pattern is not random. It is the cosmic web in motion, acting on scales so large that only careful mapping can reveal its full design. The void also influences the earliest light in the universe. As the cosmic microwave background passes through the hollow, its photons lose a tiny amount of energy. Dark energy stretches the void, while the light is still inside it, leaving the photons slightly cooler than they should be. Though the effect is small, it is measurable. It shows up as subtle temperature shifts across the sky, a fingerprint of the void, embedded in the oldest light we can see. This same influence appears when we measure distances using baryon acoustic oscillations. The cosmic ruler becomes slightly distorted inside an underdense region. Distances appear different from what they should be in a typical environment. This distortion contributes to the Hubble tension, the mismatch between local expansion measurements and measurements from the early universe. If the void raises our local Hubble constant, then our part of the universe is not a reliable indicator of the whole. This possibility forces scientists to rethink fundamental assumptions, including the long-held belief that we do not occupy a special place. In truth, the void does not make us special. It makes our environment unusual, a rare outcome of cosmic evolution, but still consistent. with the full range of what nature allows. Yet this rarity carries consequences. It means many of the measurements we depend on must be corrected for local effects. It means any theory that fits the universe must be flexible enough to explain both crowded clusters and enormous hollows. It means the cosmos is not as uniform as the cosmological principle suggests. Large structures break the smoothness we once assumed. Patterns that should average out on huge scales do not always do so. The void challenges the idea that we can describe the universe with a single number for its expansion rate, or a single density that applies everywhere. Instead, the universe becomes a mosaic, a collection of regions, each shaped by its own history, its own density, its own gravitational landscape. Understanding our void allows us to understand the universe's diversity. It helps us interpret flows, temperatures, and distributions in ways that reflect the true complexity of the cosmic web. It also offers a preview of the future. The void around us resembles what the universe will look like far from now. As dark energy grows dominant, void-like regions will expand until they define nearly everything. Filaments will thin, clusters will disconnect, galaxies will drift into permanent isolation. Studying our void today is like studying the universe's fate, billions of years before it arrives. And there is another consequence, one more subtle, yet deeply important. A civilization born inside a void sees a different universe than one born inside a massive cluster. Their sky is emptier, their expansion rate is higher, their cosmic web is thinner, their cosmology develops under different conditions, different patterns, different distortions. This raises an extraordinary question. How many interpretations of the universe exist across the cosmos, simply because different civilizations live in different environments? The void reminds us that perspective is powerful. It shapes what we measure, it shapes what we conclude, it shapes what we believe the universe truly is. Our place in the KBC void is not a mistake. It is a clue, a quiet signal, telling us to look deeper and think wider than ever before. We are not lost inside an empty region. We are positioned at the edge of understanding, in a place where emptiness reveals the universe in ways no crowded region could. The void is not a barrier. It is a teacher, and its lessons reshape everything we know. The journey through this vast cosmic void now reaches its final chapter. Across billions of light years, we trace the shape of the hollow that surrounds our galaxy. Now, standing at the end of this exploration, the message of the void becomes clear. We live inside a region defined more by absence than by abundance. The KBC void is a vast, underdense space, a gentle depression in the large-scale structure of the universe. It does not blaze with clusters or swarm with dense filaments. Instead, it stretches quietly, and its emptiness leaves measurable marks on the light and motion we observe. Inside this hollow, familiar cosmic rules take on subtle differences. Space expands a little faster here because there is less matter to slow the expansion. Gravity holds less tightly on local scales. Light travels through thinner gas and weaker gravitational wells, so photons arrive carrying a slightly different story than photons from denser regions. These effects are small on any single measurement, yet together they change how we interpret the cosmos around us. These differences affect more than numbers. They influence our estimate of the Hubble constant and our inference of the universe's age. They alter the subtle temperature patterns in the cosmic microwave background. In short, the void leaves fingerprints on every method we use to read the universe's history. But the void is not a mistake. It is an essential feature of cosmic architecture. The universe builds itself from contrast. Dense clusters concentrate matter and light. Large hollows like the KBC void hold back that matter and let dark energy act more freely. Both extremes are necessary to form the cosmic web that binds the universe together. Beyond the void's edge, the universe becomes thicker and louder. Filaments sharpen into long chains of galaxies. Superclusters gather like great cities of stars. Hot plasma fills the space between galaxies and clusters and glows in X-rays. Supermassive black holes sit at cluster centers and launch jets that sculpt their surroundings. Gravity is the dominant actor in these places, driving mergers, stripping gas, and igniting intense star formation. The contrast between interior and exterior is instructive. Inside the void, galaxies evolve slowly. They merge rarely. They retain their gas for long periods and form stars at a steady, gentle pace. Outside the void, galaxies are battered by interactions. They transform quickly. They grow massive bulges and central black holes. Environment shapes destiny across cosmic time. The void also offers a laboratory for studying dark energy. Where matter is scarce, dark energy's influence is clearer. The void's expansion history reveals how dark energy acts when gravity is weak. By measuring the growth and shape of voids, astronomers can test whether dark energy is a constant property of space or whether it changes over time. These measurements provide one of the cleanest windows we have into the nature of cosmic acceleration. The void's effect on ancient light is another key lesson. Photons from the cosmic microwave background pass through this region on their way to us. Because the void expands while the photons cross it, they lose a tiny amount of energy, leaving a small cooling signature. That effect confirms the void's presence and helps map its depth and size. Looking forward, the void reveals the universe's likely future. Dark energy will continue to accelerate expansion, and regions like this one will grow relatively emptier. Filaments will thin, and clusters will recede from one another. In the distant future, observers inside any bounded group of galaxies may see a sky bereft of external galaxies. The cosmic web will fade into isolated islands of matter surrounded by an ever-expanding dark. This long-term fate gives urgency to present observations. We live in a fortunate era when the cosmic web is still visible and accessible. Future astronomers many billions of years from now may find far less evidence of the universe's grand past. Their sky could be dominated by the merged remnants of their local group, with the microwave background redshifted beyond detection. The void also raises philosophical questions about perspective and typicality. If environments differ across cosmic space, then so too may the views of any civilization that arises in them. Observers inside dense clusters and observers inside deep voids would draw different cosmological conclusions from the same laws of physics simply because of their locations. Our measurements are local by design, and recognizing that locality helps us correct our models and broaden our understanding. In practical terms, the presence of the KBC void demands careful work. Astronomers must map the velocity field of nearby galaxies, refine distance measurements, and extend surveys beyond 2 billion light-years. They must compare observations inside and outside the void to separate local biases from global truths. Upcoming telescopes and surveys will provide the depth and precision needed to make this separation reliable. The void's existence also reminds us of the power of chance in cosmic history. Tiny irregularities in the infant universe, stretched by inflation and amplified by gravity, produced the rich architecture we see today. Those same random ripples made it possible for our region to evolve the way it did. We are, in that sense, the product of both law and chance. As this documentary closes, the final message is simple. The universe is stranger and more beautiful than a uniform picture ever allowed. Emptiness is not absence, but a form of structure. It shapes motion, light, and time. It provides a stage on which gravity and dark energy act in full measure. We live inside a cosmic hollow that teaches us how the universe behaves when matter is rare. That hollow bends our measurements, but it also offers a clearer view of the forces that shape everything. It is both a challenge, and an opportunity. The story of the void is not the end of cosmology. It is an invitation to look farther, measure more precisely, and accept that the cosmos will always hold surprises beyond the edge of our current understanding. The void asks us to keep exploring, not because the universe is failing to make sense, but because it is richer than we ever imagined.